Okay, so my name is Matt Mahlin. I'm at Langley. Thank you for the introduction. I'm the principal investigator for the Tall Lunar Tower project, and we started this just about a year ago under Project Polaris, which is advanced exploration system initiative for early career and other teams to begin development of impactful research or technology development for lunar surface operations. Um, So the Tall Lunar Tower itself is an in-space assembly team that we aim to design, build, model, fabricate, constantly assemble, and characterize a Tall Lunar Tower engineering development unit. So we're working on demonstrating our assembly approach for this uh, truss tower technology. This is a cross-cutting truss assembly technology that will be developed, enabling construction of infrastructure in the lunar environment. And right now we're focusing on tall towers. And why a tall tower? The fact is, when you get greater than about 50 meters in height for solar arrays, you can significantly reduce lunar night to just 2 days and significantly reduce battery mass. And if you look at my chart here, you can see the topography of an area around Shackleton Crater. It's the connecting ridge, and it's kind of the tall mountain in the area. It's about a area about 2 kilometers by 2.5 kilometers. And if you start looking at the charts in the center, you can see about 2 meters in height, all the red, you get about 14 Earth days worth of lunar night. And then you get this thin ridge in the middle where you've got about 2 Earth days of lunar night in some spots. And it's very difficult to keep your solar panels illuminated in that at that height. But you start seeing a significant knee in the curve of your Earth days of lunar night at about 30 meters, and then up to 50 meters, uh, it's you see a much wider area where you can sustainably or consistently collect your solar power. So that's why building upwards is really desirable for solar arrays at the lunar South Pole. And here our project focus is on developing that robotic truss assembly technology applicable to a tower. And the tower truss structure is just one thing that we hope to uh, that we're applying to, and in the future we'll be looking at other sorts of structures. But our objective here is that set it up so we have compact packaging for launch. We will be doing robotic assembly with supervised autonomy. 50-meter tower is the target. Then high payload capacity, we want to be able to hold about 1,500 kilograms with a high safety factor, so we can support 100 kilowatt power or greater, communication, and more, and potentially science missions. So with this, we want to enable extreme surface access, lunar construction, and we're also studying ISRU for components as a pipeline that if we have this assembly technology, we can potentially utilize components built on the lunar surface to build multiple towers. So a little bit about our work that we've been doing here before we go to the next slide is we built a truss configuration utility, uh, and this kind of gets us a sizing of our tower before we go into more detailed FEA and other evaluations. Then we can estimate our payload mass that we can support, and we look at the lunar payload capability and the Earth payload capability, because we want to demonstrate this on the Earth first. So it is strong enough to support itself on Earth. And then we've also been looking at the thermostructural analysis, what sort of temperature extremes a structure of this type will have to endure. So we'll talk a little bit more about that. Next slide, please. Okay, so one of the great things about building upwards is that you can reduce your tower, your battery mass. So if you had a shorter tower, you would have to have, to survive the lunar night, you'd have to charge massive batteries to discharge while you uh, stay warm through that lunar night. So tower mass versus batteries is something that we analyzed. And if you look at the bottom here, we have the longest darkness periods, and looking at that one site that we looked at multiple. and we looked at multiple heights. And you look at the chart on the right, or the graph, you see that connecting ridge site, and you look at the 3 lines, you can see these are the lines for longest darkness periods, and this yellow one is the most extreme, where if it's smoothed out so that you have a period of light less than 24 hours, it just smooths over it. While the other 2 are looking at solar disk peaking above the surface or the horizon, that it doesn't smooth out those less than 24-hour sunlit periods. But with these, you can see some interesting points that point us towards about 30 meters, 50 meters height being desirable for that area. So looking at the battery versus tower mass, we use an assumption that battery energy density was about 150 watt hours per kilogram, and that Artemis Base Camp darkness power demand would likely be on the order of about 5 kilowatts or greater. And for the sites evaluated on the connecting ridge, we found that taller tower means less system mass overall if the darkness power exceeds about 1800 kilowatts. So if you look at the bottom right chart here, you can see the thin blue line on the left shows that more battery is better if you need less than 1800 watts to survive the lunar night. But if you need more, you should get a taller tower, and you can have significant reduction in mass in your system. Okay, next slide, please. Okay, so a little bit about the Truss configuration utility. So we developed this at Langley, and we used it to assess the preliminary design and structural requirements for lunar load cases. This TCU is based on 3 governing equations: the Lagrange Euler buckling, so the individual members, the complete tower Euler buckling, and the mass of the tower. So the governing equations there, we can change our inputs and get different outputs to help us figure out that the mass of the tower, the length of strut for each bay, and other modeling parameters. We can look at different materials, we can look at different cross sections, and it's a really quick tool for us that we use to pick our height and our truss section. Then after that, we go into detailed thermostructural analysis of the tower with these parameters. And you can see on the right a preview of what our configuration utility looks like. And next slide, please. So the concept that we're driving towards here is the first iteration of this is a lander-based mission, where we would bring our entire system on the back of a lander. It would deliver all the components and the robotics, and then 2, it would remain on top of the lander deck. So being able to take this and put it on a rover or mobility platform and is another step that we'd want to develop. But for the first run proving the system, we'd probably keep it on a lander. Then it would have to be powered to run the robotics. Then you start the assembly of repeatable truss bays. So you see in the middle here, starting to append truss bays to the bottom and lifting the tower up incrementally as new bays are completed. And this is possible because the tower mass itself is only about 110 kilograms, even at that 50-meter height. Then once you get to your max height, you would lift your solar panels to the top with a payload hoist, or you would have had your solar array. Option 2 would be have the solar array or payloads on top as you are lifting. Then you need to deploy your solar panels and then connect to the power grid. And about 100 kilowatt array is about 50 meters by 26 meters. Okay, next slide, please. So in our project for last year, our key hardware development, we've been focusing on our truss assembly and outfitting frame that sets up the bay size by jigging it, and then 2 bespoke joint and associated end effector. So you see on the right side, Then 3 rivet joint and associated effectors. So we've got 2 joint technologies that we're currently working on down selecting. And we focused on fasteners at the moment because it's easier for us to work with in the lab. We're also evaluating in the future, moving towards things like welding. So that is also under consideration. Then for our parallel joint development, the bespoke joining system, we're looking at this one because it's optimized for robotic assembly. We have a single screw per joint, then integrated assembly guide features with captured fasteners. So they kind of puzzle piece together as a robotic arm would put them in place. And you can also see on the top right, kind of our side frame assembly sequence that we're looking at, where it's partially modularized, and you have side frames with diagonals in them that are put on opposing sides on one level or story of the truss structure, and then on the next story it would alternate to, say, front back to left right, and then populate the diagonals. So trying to reduce the assembly steps as much as possible. Then for the rivet joint system, we're looking at really simple joints that are made from sheet metal. So they would hopefully be ISRU compatible. And there's an increase in tool complexity and rivet management required to deal with this. And for this, we're looking at cross-frame assembly sequence, which is another way of modularizing. One main difference between these two is the bespoke joint requires kind of splitting your joint in halves, while the cross-frame assembly is all your members are coming into a full joint. Okay, next slide, please. So a little bit about our engineering development unit that we're working on. And our goal is to, for this 2-year project, is to do a full-scale demonstration. So we built a simple, kind of a really quick version of our jigging system that it's not flight-like, but it kind of performs the same tasks. And you look on the left, you can see this construction robot system, the CRS, which is this jigging frame. It has the interfaces to grab the truss nodes and to lift them up. Then the assistant robot systems. Right now we're using UR10Es to hold our end effectors, manipulate our truss components, and fasten truss members to the bottom of the truss structure, and then package trusses. So right now we're using carbon fiber struts with aluminum ends. And the system would be compatible with using all aluminum if given ISRU components. That's the idea. You can kind of see we're working on emulating the system on the back of a lander, as I mentioned, and for Earth testing, we would be doing about a 300. We would be doing a smaller, reduced payload size, but about 100 kilowatt array is about 325 kilograms. It's a 50-meter tower, 1 meter by 1 meter by 1 meter bays, 110 kilograms. And if you look at Lunar Starship, it's about the same height. And on the right here, this should be an animation. If you could play it. There you go. You can see this cross-frame assembly sequence where you are adding in the cross frames, then you're populating the verticals and diagonals, and then you increment upwards and start building one at the bottom. And this avoids redundant members and just repeated assembly here. Okay, next slide, please. Okay, I think this is my last slide. So this kind of evolution that we're going for is first, we would like to do a CLIPS mission, potentially 25 meters, smaller power generation and communication capabilities, all delivered. We would need some sort of robotic arm to be on our system or co-manifested. Then 2, potentially having our own lander dedicated where we could build a larger structure and carry that large solar array. And then 3, we would want to have a mobile system where it can be placed on a foundation, such as Mark Hilberger was talking about, and be able to use that sort of earth moving technology, build our foundation, build on top of it, bring our system in on, say, a rover, use it there, and then pull it back off the assembled tower, and then go to a new site. And eventually, the 4th step here would be using an ISRU supply chain and using all aluminum components. And I believe that is my last slide. Thank you.
Thank you, Matt.